All right, this is the video for Notes 9-2, Test Statistics and P-Values. So here's an example that we're going to kind of work with in this lesson. You play a game where if you pull out a red card from a deck of cards, you win $100. You watch 50 people play the game, and only 15 people win, meaning 15 people draw a red card. You suspect that the game maker is using a weighted deck, meaning one with less than 50% red cards. So here's your null and alternative hypothesis. The null hypothesis would be basically that the deck is fair, so the deck has 50% red cards. Your alternative hypothesis is basically what you're trying to show. You suspect that there's less than 50% red cards. So P is less than 0.50, where P represents a proportion of red cards in the deck. The whole idea of hypothesis testing or significance testing is we want to know, based on the evidence that we collected, that 15 out of 50 people selected a red card. Is that enough evidence to basically prove what we're trying to prove, that the proportion of red cards is less than 50%? So if we compare this to what we think it should be, 15 out of 50 is 30%, right? 30% of the cards were red. Whereas we think that the deck should be 50%. So we have to ask ourselves, I mean, we know that that's possible. It is possible to only draw out 15 red cards out of 50. However, we want to know how possible is that, given that we're going to assume that the deck is fair. So that's the whole idea of hypothesis testing. So in terms of the steps, a lot of these steps are going to look familiar. So step one, we're going to identify the symbols. We'll get more into this tomorrow. Step two, we're going to state our hypotheses. We learned how to do that yesterday or 2 days ago. Step three are to check the conditions, which is going to feel very familiar. Step four, we're going to do the calculations. So we're going to calculate a test statistic and a p-value. This is similar to what we did in Unit 7 with sampling distributions. And then step five, we're going to give our conclusion in context. So the reason why these are bolded and italicized, because those are the steps that we're going to focus on today. So let's make sure, so in step four, we talk about test statistics and p-value. So let's talk about what is a test statistic, and then we'll talk about what a p-value is. So a test statistic can be either Z or T. So these letters should look familiar. We use those in confidence intervals. For a Z test, which is what we're going to use for proportions, and then means when our sample size is large and sigma is given, the Z test or the Z test statistic is essentially a Z-score. So to remind you from Unit 2, a Z-score, which in this case, a test statistic, is going to tell us how far away our statistic is from the mean, which is our null hypothesis. So if we think about this distribution, right, in the middle is going to be our hypothesized value, whatever it says in the null hypothesis. So for our example of the deck of cards, this middle is going to be mu equals, or P equals 0.5. Our test statistic, we're going to find our what it is, and that's going to tell us how far away we are from the mean, okay? The larger our test statistic is, so meaning either in the negative or the positive direction, the larger it is, the farther away it is from the mean. Basically, if you have a large test statistic, that means whatever result we saw is very far from the mean. So for instance, if this is 0.5, right, 0.330, which is what we got in our example, is somewhere out here. That's pretty far from the mean. The test statistic tells you how far away it is, how many standard deviations away it is, and then we're going to use the test statistic to calculate the p-value. So a p-value, this is the definition of a p-value. P-value is the probability computed assuming our null hypothesis is true, that the observed outcome would take a value as extreme as or more extreme than that actually observed. So this is just the verbatim definition. I don't really want you to worry too much about that. Here's kind of the general idea. The basic idea is if we have a small value, a p-value, that's evidence against our null hypothesis, because the observed result is unlikely to occur if our null hypothesis is true. So again, going back to this example, if our null hypothesis is 0.50 and 0.30 is all the way out here, that p-value is going to be pretty small, right? It's going to be pretty small. The area under to the left of it is pretty small. That's telling me that I have evidence against our null hypothesis, because the chances of me getting only 15 out of 50 cards if the deck is truly fair is probably unlikely. If we have a large p-value, that fails to give convincing evidence against our null hypothesis and in favor of alternative, because they say that the observed result is likely to occur by chance alone when our null hypothesis is true. So you can think of the p-value as the chance of that happening if our null hypothesis is true. The smaller the chance, the more evidence we have that our null hypothesis is not true. Okay, so small p-values give us evidence against our null hypothesis. Okay, so to give you a concrete example, going back to our example again, here's our null and alternative hypothesis. P represents the proportion of red cards in the deck. This is the test statistic. We're going to learn how to calculate that tomorrow. Z equals negative 2.83, so that tells me it's almost 3 standard deviations below the mean. To find that probability, we're going to do the same thing that we did in our z-score unit. So I'm going to open up my z-table. Since we're looking for less than, that means I can just take the value from the table. So we're looking for z is less than negative 2.83. So negative 2.80123, that p-value is 0.0023, 0.0023. So what does that mean, right? Here was our null hypothesis, here was our alternative hypothesis, and this is what we found, right? Based off the test statistic, our p-value is 0.0023. So we have to ask ourselves, is that small or big? That's really small. Essentially, what this is saying is if our null hypothesis is true, meaning the deck is fair, there's only about a 0.23% chance, I put that in quotes because I don't really like the word chance, but it's something that people tend to understand, a 0.23% chance that only 15 red cards would get pulled in a random sample of 50 cards when drawing with replacement. That's very, very, very unlikely. Meaning if that happened, that means that maybe our original claim is not true. Maybe our original claim is false. So that small p-value gives us evidence against our null in favor of our alternative. Because this is so unlikely to happen, 15 out of 50, right? This is the likelihood. Because that is so unlikely to happen, that indicates evidence that maybe our alternative is true, that the proportion of red cards is less than 50%. So what do we conclude? Okay, so we have to ask ourselves, okay, how good is that evidence? Well, to give a kind of a concrete answer, we have what's called significance levels, which is we use with the symbol alpha. So this is the symbol, Greek symbol alpha. It is a predetermined decision point. So old school statistics says to use alpha of 0.05. I'm just going to use that for the sake of simplicity. If a problem doesn't state an alpha level, you should just use 0.05. That's kind of a good middle of the road significance level. If it states a different significance level, you should use that. So the problem will either state it. If it doesn't state it, you use 0.05. So what we do is we compare our p-value to that alpha. Well, our p-value is either going to be below or above the alpha. If our p-value is below or less than alpha, our decision is to reject our null hypothesis, because remember, small p-values give us evidence against our null, so we're going to reject it. And what we conclude is that we have statistically significant evidence that the alternative may be true. If our p-value is greater than alpha, so it's above 0.05 or whatever your alpha level is, we fail to reject our null hypothesis. So these are the decisions we might make. We either reject or we fail to reject. When we fail to reject, we conclude that we do not have enough evidence to support our alternative hypothesis. So again, going back to our example here, remember our p-value is 0.0023, and if we're using an alpha of 0.05, this is what our conclusion would look like. Since our p-value, 0.0023, is less than alpha of 0.05, we reject our null hypothesis, or HO. We have statistically significant evidence that the proportion of red cards in the deck is less than 0.50. So here's kind of a template for writing your conclusions for when you either reject or you fail to reject. So when we reject, we say since our p-value equals, and we need to state the p-value, and we say that it's less than alpha of, again, whatever the alpha is, we reject our null hypothesis. We have statistically significant evidence that, and then you just need to state your alternative hypothesis in words. If you're failing to reject, this is what your conclusion looks like. Since our p-value equals whatever is greater than alpha, because you fail to reject when it's greater, we fail to reject our null hypothesis. And then you say we do not have enough evidence to conclude whatever the alternative was. So notice in both cases, we're stating the p-value, the alpha level, and the alternative hypothesis in words. However, the difference is we're either rejecting or failing to rejecting, and either we have statistically significant evidence or we do not have enough evidence to conclude whatever the alternative is. We never accept the null hypothesis, because remember, the null hypothesis is what we're already accepting to be true. We either reject or fail to reject it. All right, so just going through some examples. Here's an example. I'm not going to read it, but I'm going to state that the resulting p-value is 0.1404. It says, if you are using alpha of 0.05, would we reject or fail to reject? Well, this is the p-value that is greater than alpha. So in this case, we're going to fail to reject our null hypothesis. So based off of that, what do we conclude? Well, when we fail to reject, I'm just going to say it verbally. Since our p-value is 0.1404 is greater than alpha of 0.05, we fail to reject our null hypothesis. We do not have enough evidence to conclude that the mean daily calcium intake in the population of teenagers is less than 1,300 milligrams per day. So again, I'm just putting in context. That's the alternative hypothesis in words. All right, here's another example. Again, I'm not going to necessarily read it. We're going to look at the p-value. P-value is 0.0729. It says, if you're using an alpha of 0.10, would you reject or fail to reject our null hypothesis? So again, comparing our p-value to our alpha, this is less than alpha. So in that case, we are going to reject our null hypothesis. So that conclusion in context, when we reject the null, we're going to say, since our p-value 0.0729 is less than alpha of 0.10, we reject our null hypothesis. We have statistically significant evidence that the mean lifetime of the new deluxe AAA batteries is greater than 30 hours. All right, and this last example, we have a p-value of 0.0423 and then alpha of 0.05. Would we reject or fail to reject? In this case, we compare this to alpha. That is less than alpha. In this case, we're also going to reject our null hypothesis. Since we're rejecting our null hypothesis, what we're going to conclude is, since our p-value is 0.0423 is less than alpha of 0.05, we reject our null hypothesis. We conclude that the proportion of potatoes with blemishes in a given truckload is greater than 0.08.